learning competency here is to describe how rocks behave under different types of stress, such as compression, pulling rocks by stress, and undergo solid deformation, and to explain how tension, compression, and shear stresses produce geological features. Okay, let's go. Let's compare and contrast these two pictures. I will give you 1 minute, so pause this video and write down your answer. So the first picture, we can say that this is undeformed or unstrained because, as you can see, the lines are organized, right? We can say that the strata occurs in horizontal layers. The sand grains are spherical. You can see that in the circle here. And there's no faulting or faulting. There's also no metamorphic rocks, but there's a few joints observed. In the second figure, we can say that this is deformed or strained. As you can see, layers are tilted. The rocks are highly folded and possibly metamorphosed. That's what we discussed in the previous video. The grains are squashed or distorted. Lastly, there is fault with large offset juxtaposed different rocks side by side. So we can say that the second picture undergo deformation. So what is deformation? It is any process that affects the shape, size, or volume of an area of the Earth's crust. So the type of deformation that occurs depends on the type of stress and the type of rock present. Now, we have talked about stress and strain. Stress is a force acting on a material that produces a strain. And if you remember, strain is the change in shape or volume of the rock that experienced stress. Stress is applied over an area and therefore has units of force over area, like Newton meter squared or pounds per inches squared. Okay? And if you remember in physics, the formula for pressure, and Newton per meter squared is actually the SI unit of pressure, which is Pascal. Now let's talk about pressure. Pressure is a stress where the forces act equally from all directions, right? So we called it uniform stress. But here we're going to call it confining stress, as shown here in the diagram. Now we also talked about differential stress. This is when the stress is not equal from all directions. Now there are three different kinds of differential stress. The first one is the tensional stress or the extensional stress. So it stretches the rocks. The compressional stress squeezes the rocks. And lastly, the shear stress. Shear stress results in slippage and translation. So when rocks deform, they are said to strain. This table shows you the difference between stress and strain. But the most important here is that stress is resisting force per unit area and strain is deformation per unit area. Also remember that stress can exist without strain. Strain cannot exist without stress. To make it simple, just remember that stress is the cause and strain is the effect. Okay? By the way, when you say resisting force, it's like the applied load in physics. Okay? Now let's go to deformation. Deformation has two kinds, elastic and inelastic. Now to better understand the concept of deformation, let's have some common things. So first we have this rubber band. So a rubber band is a material that returns to its original shape once the stress that deforms it is removed. Right? So when you pull the rubber band, then you release it, goes back to its original form, unless you pull really hard. Right? Now, we say that it's inelastic when a material does not return to its original shape after it is formed. And there are two kinds of inelastic materials, the brittle and the ductile. Okay? When we say brittle, they respond by breaking and fracturing. So it gets destroyed. Okay? One example is clay. When we say it's ductile, it responds by bending or deforming, but without breaking. Okay? It's just deformed. One example is a metal wire. When a rock is subjected to increasing stress, it passes through three successive stages of deformation. Okay. The first one is the elastic deformation. Here, the strain is reversible, so meaning it can go back to its original form, just like the rubber band. Next, we have the ductile deformation. Here, the strain is irreversible. You cannot change it again. It cannot go back to its original form. Then we have the fracture. It's a reversible strain wherein the material breaks. So as you can see here in this graph, as the stress increases, the strain increases. So the material has an elastic limit. So it is only elastic until here. And when you exceed threshold, it will become a ductile deformation, meaning it will not go back to its normal form. Okay, here. Then when you reach this point, this is the time that the material will break. Okay. Remember, little materials. They have a small or large region of elastic behavior, but only small region of ductile behavior before they fracture. Okay, so again, it's very elastic at some point, then after you exceeded the elastic limit just a little, it will fracture. This is described by this graph. So low temperature, low confining pressure, and high rate of strain enhance the brittle properties of rock. Next, we have the ductile materials. So they have a small region of elastic behavior and a large region of ductile behavior before they fracture, meaning you can only stretch it to a minimal point where it turns to its original form. But the range between the elastic limit and the fracture are very wide. It doesn't fracture easily. This is best described by this graph. Remember, high temperature, high confining pressure, and low rate of strain enhance the ductile behavior of rocks. Okay, take note that the composition of a material determines the point at which brittle ductile transition occurs. So it depends on the composition. Okay, now how a material behaves will depend on several factors. First, we have the temperature. So at high temperature, molecules and their bonds can stretch and move. Therefore, materials will behave in a more ductile manner. Okay, remember, high temperature, more ductile. Consequently, at low temperature, materials are brittle. Okay, very easy. We have confining pressure. So remember, confining pressure, the pressure or the stress is equal in all directions. At high confining pressures, materials are less likely to fracture. On the other hand, at low confining pressure, materials will be brittle and tend to fracture sooner. Okay? High confining pressure, low chance of fracture. Low confining stress or pressure, brittle, and fractures sooner. Next, we have the strain rate. Remember, at high strain rates, materials tend to fracture. So at low strain rates, more time is available for individual atoms to move. Therefore, ductile behavior is favored. Lastly, we have the composition. Some minerals like quartz, olivine, and feldspar are very brittle. Others like clay minerals, micas, and calcites are more ductile. This is due to the chemical bond types that hold them together. Therefore, we can say that mineralogical composition of the rock will be a factor in determining the deformational behavior of the rock. Another aspect is presence or absence of water. So water appears to weaken the chemical bonds and forms films around mineral grains. This causes slippage to happen. Thus, wet rock tends to behave in ductile manner, while dry rocks tend to behave in brittle manner. Okay, so remember in chemistry, water is the universal solvent. Also, water plays an important role in magma formation, right? So see, it's all connected between confining pressure and strain. So the y-axis is the amount of pressure to deform a material, measured in MPa. The x-axis is the amount of strain or deformation needed. Only in a few cases does deformation of rocks occur at a rate that is observable on human timescales. Abrupt deformation along faults, usually associated with earthquakes, occurs on a timescale of minutes or seconds. On the other hand, gradual deformation along faults or in areas of uplift or subsidence, like subduction, can be measured over periods of months to years with sensitive measuring instruments. So basically, humans can't feel it right away. You need to have a machine. Okay? So what are the evidences of deformation? The evidence of deformation that has occurred in the past is very evident in crustal rocks. For example, sedimentary strata and lava flows generally follow the law of original horizontality. Thus, when we see such strata inclined instead of horizontal, it is an evidence of deformation. Okay. Since many geologic features are planar in nature, we need a way to uniquely define the orientation of planar feature. We first need to define two strike and dip. For an inclined plane, the strike is the compass direction of any horizontal line on the plane. It is the direction of the line formed by the intersection of a rock surface with a horizontal plane. The dip is the angle between a horizontal plane and the inclined plane. This is measured perpendicular to the direction of strike. So here it is. In other words, dip is the acute angle that a rock surface makes with a horizontal plane. Remember, strike and dip are always perpendicular to each other on a map. So this picture will help you understand what is the line of strike